let's begin by looking at your feedback from last week. So there were various comments which I'll respond to, but first of all, I noticed that somebody said that they really like Professor Bakshi, maybe more so than me. Well, that's I'm a little bit jealous, but it's good to hear that that people liked Professor Bakshi. Yeah, I agree. He has a very clear way of explaining, so I'm glad to hear that. Um, all right. Also, I notice. I mean, I remember from previous years that week 5 materials are quite challenging. Okay, so some of you I've just seen of around campus, and you've already said, "Oh, week 5, I'm having trouble understanding it," and so on. So this is not you are not alone. Like basically, what I want to tell you is many of your classmates are probably also having trouble. Okay, I just posted this poll. Feel free to participate if you'd like. I just added a new option, like everything is fine, but I noticed very few people have signed up for it. Okay, so so the basic message is week 5, along with week 8 and week 11, is probably the toughest. Okay, these are extra materials. These are materials that are not being covered in the usual class in ENGG 1410. So, you're lucky, right? You're lucky that you have this extra material. You're also lucky because some of these materials, like singular value decompositions, Jordan canonical forms, these are actually quite useful from an engineering perspective. Like once you know how to use singular value decompositions, it'll be very good because these will come up in some context, and you will have already seen it before. Okay, so there's a reason why we are making you do these things. Oh, people are updating it. One person has just said everything is fine, so that's good. So there'll be someone to help you during the mate system on Friday. All right. Okay, good. So let's look at today's lesson. I'll do a quick review of the concepts. So we'll do that shortly. But before that, let me also highlight that this week's exercises are slightly different. So even though there are 5 calculation-based questions, like slightly more basic questions, we will still allow you to get bonus points for posting any solutions on Piazza. So for any of the first 9 questions, if you post on Piazza, indeed any of all the questions on Piazza, in the sheet, if you post on Piazza, you will get bonus points. Okay, not just for the more conceptual questions, even for the more calculation-based questions, you can get bonus points. So TAs, please note there should be a thread on Piazza for each of the first 9 questions. Okay, so not just questions 6 to 9, but questions 1 to 9. There should be a thread on Piazza. And can you please post those threads on Piazza? Okay, so before we start, so it's already clear based on your feedback that many of you are having trouble with some of the concepts, and in this review session, I can't really hope to clear up all your doubts. So we have the rest of the week for that, right? But at least let's make sure that basic definitions are clear. Maybe not the full proofs, but let's make sure that the basic definitions are clear. Okay. So first of all, what's a unitary matrix? A unitary matrix is something that satisfies U dagger U is equal to U dagger is equal to identity. Okay, and this should remind you of orthogonal matrices which satisfy U transpose or O transpose O is equal to O transpose is equal to identity, right? For an orthogonal matrix, you have some identity like this, that the transpose of the matrix is its own inverse. Here, you have to take the transpose conjugate. So this dagger just means that I take U transpose and then the conjugate of this matrix. That's what U dagger means. Okay, so this is a generalization to complex matrices of orthogonal matrices. And just like orthogonal matrices are somehow like choosing a different basis for your vector space, unitary matrices are also so orthogonal matrices are rotation matrices. They rotate to a new basis. Similarly, unitary matrices rotate to a new basis, but now with potentially complex numbers. Okay, So in some sense, they are the natural objects, natural generalizations of orthogonal matrices to complex spaces, to complex vector spaces. Okay. There are other properties and so on, but we won't go into them right now. This is at least enough to get you started about unitary matrices. Okay. Okay, orthogonal complement. So what's an orthogonal complement? The orthogonal complement of a vector space V in a vector space W. So suppose V is a subspace of W. Suppose both of these are vector spaces, and V is a subspace of W. So the orthogonal complement of V in W is some other vector space U, such that like if we wanted to draw it pictorially, let's imagine that this is W, but there's some vector space V in here, another vector space U in here, such that linear combinations of vectors in U and V will span the whole space W. Okay. So for example, the vector space U could be the vector space spanned by 1, 0, 0. This could be U. V could be 0, 1, 0, and then W would be anything which is, which is of the form AB 0. Okay. And it's important for U to be the orthogonal complement of V inside W. It is important that every vector in U is perpendicular to every vector in V. Okay. So the orthogonal complement is somehow, it's like the basis vectors that are required to complete the vector space V to get to the vector space W, and also such that the basis vectors in U are perpendicular to the basis vectors in V. Okay. So somehow they are orthogonal to each other. That's why it's called the orthogonal complement. Okay. And again, there'll be an exercise to help you calculate this and get used to it. So we'll get there. Okay. Spectral theorem. So there were two spectral theorems in the notes with the proofs, and I understand that the proofs may have been somewhat complicated. Some of you certainly had some trouble with the proofs. But let me remind you what the important points of the spectral theorems are. Okay. So in class, or in the videos, what did we prove to you? We proved to you that if you have a Hermitian matrix, and what is a Hermitian matrix? A Hermitian matrix is basically a generalization of a symmetric matrix. Okay. A Hermitian matrix is just like a symmetric matrix, but with complex entries. So a Hermitian matrix has the property that the dagger of the matrix is equal to itself. Okay. And remember, the dagger, that is the transpose conjugate of a real matrix, is just the transpose of that matrix. Therefore, a symmetric matrix by definition is Hermitian. Okay. So for Hermitian matrices, what property do we have? We have that that there exists. So if you have a n by n Hermitian matrix, there exist n eigenvectors, n orthogonal eigenvectors. Okay. Even though it may have repeated eigenvalues, so even if the matrix has repeated eigenvalues, even then a Hermitian matrix has the property that it must have n orthogonal eigenvectors. Okay, so it has full geometric multiplicity. It has as many eigenvectors as the size of the matrix, and this is quite important in some applications. So, and indeed, one of the exercises today is to generalize the spectral theorem to so-called normal matrices. Okay, I'll show you that exercise question shortly. So this will be a generalization in today's exercise sheet. Okay. All right. 3 more concepts. So what's a Schur decomposition? So a Schur decomposition says, suppose someone gives you a matrix M, any n by n matrix, you can always write it as a unitary matrix times the upper triangular matrix times the unitary matrix dagger, unitary matrix transpose conjugate. Okay, transpose conjugate. So this thing here is basically saying that any matrix is, let me just say it again, is a unitary matrix times the upper triangular times the unitary matrix transpose conjugate. Okay, so one way of thinking about that is, suppose you have a diagonalizable matrix. So suppose you have a diagonalizable matrix, unitarily diagonalizable matrix. So that would mean M can be written as U, then some diagonal matrix U dagger, right? So last week, with Professor Bakshi, you saw that if you have, for example, n distinct eigenvalues, then the matrix is diagonalizable. You can write it as a unitary matrix times a diagonal matrix times the transpose conjugate of that unitary matrix, right? And what is the physical meaning of such a matrix? So unitary matrices, like we just said, are like rotation matrices, right? So diagonalizable matrices are very special. What are they? They're like your matrix. Your matrix is basically a rotation, a stretching, and then a rotation back, right? So geometrically, what this is saying is, if you have a diagonalizable matrix, then you're rotating by U, you're stretching by D. What does stretching by D mean? Like the first vector gets stretched by the first eigenvalue, the second one gets stretched by the second eigenvalue, and so on, right? And then you multiply by U dagger, which is like rotating back, right? Because U dagger is U inverse, which is rotating back, which is geometrically a very useful fact to know, right? But if you have a diagonalizable matrix, then it is the same as doing these three operations successively, right? Now, not all matrices are diagonalizable, but the Schur decomposition tells us that every matrix has this property. You can rotate, you can do this upper triangular business, which is more complicated than multiplying by a diagonal matrix, right? But nonetheless, it's something, and then multiplying by U inverse, okay? So that's what geometrically, that's what the Schur decomposition is telling us. And again, in your in the exercise, we'll ask you to calculate some Schur decompositions. We'll ask you to basically do some calculations based on Schur decompositions. A special case of a Schur decomposition is well, okay, so using Schur decomposition, it can be shown, and this is actually the only thing that in the videos we state a theorem without proof, right? In the videos, I claimed without proof that every square matrix can be written in Jordan canonical form. And as a Harold exercise, I will, like the last question in today's exercise sheet is to prove that statement. But what does the Jordan canonical form say? It says that any matrix M can be written in the form U and then Jordan blocks. So what are Jordan blocks? Something which have blocks over here, and each of these blocks looks like it has the same lambdas along the diagonals, and then ones in the super diagonal, and then zeros everywhere else here, right? Something like this. Each of these is a so-called Jordan block, and everything else is a 0 times U dagger, right? So the Jordan canonical decomposition says that even if a matrix is not diagonalizable, right, you can always write it in an almost diagonal way, such that the elements along the like close to the diagonal form blocks, and there are the same lambda values in each of the blocks along the diagonals, and then there are ones above it. Okay, there are ones, or so some of these lambdas may be the same, some of these may be different, and you saw in the video examples of some Jordan canonical forms. In one of the keep exercises, we asked you to also compute a Jordan canonical form. So again, you'll get an exercise to try to compute the Jordan canonical form of a matrix, and you'll see that as well. Okay. Finally, what is maybe the most useful, well, along with unitary matrices, maybe the most useful thing that you'll have that we'll have taught you is singular value decomposition. So given an arbitrary matrix, not necessarily square, so suppose someone gives you a matrix which is a m by n matrix, the singular value decomposition is going to be basically mm transpose, and then find the eigenvalues and eigenvectors. So eigenvalues and eigenvectors for for this MM transpose. Okay, and there is a physical significance for these eigenvalues and eigenvectors. The eigenvalues somehow represent the energy along along certain directions for this matrix. And often when someone gives us a lot of data and we want to try to cluster this data, try to see if this data is more in some locations, less in some locations, one of the things that we do with this data is to write it in a matrix form, try to do a singular value decomposition. So this is a very useful technique in data analysis, especially with large data. And you'll maybe see, and we already showed you an example in video number 50 of how to do data compression via singular value decompositions, right? So that's the utility for that. Okay, now again, if you had trouble understanding the proofs in the videos, that you already know based on the poll that many of your classmates already did, right? So let's not worry. Okay, this week our goal is to first of all understand how to calculate with these things, right? And then via the exercises and also via the mate system and talking to the TAs and talking to me and so on, together we'll try to make sure we understand the concepts as well. Okay, try to make sure we understand how to prove these things related to each other. All right. So at this point, the TAs are going to distribute the exercise sheets. Actually, before I do that, let me. I mean, I know it's usually uncomfortable being the person trying to ask questions, but if you do have some questions, this is a good time to raise your hand to ask questions. So if you have any questions about any of these concepts that were in week 5, this is a good time to ask, or at least to think about it. And then when the TAs and I are walking around, you can ask us. Okay? Any questions? You look like you have a question. Yes.
CHUR decomposition, why T has to be an upper triangular matrix?
Okay, so the question being asked, which is a good question, is in the Schur decomposition, why does T have to be an upper triangular matrix? Okay, so as so the decomposition starts off by saying that any matrix can be written in a form unitary, upper triangular, unitary dagger. Okay, so that is in some sense the definition. The fact that it can be written is the non-trivial part, right? Now this is not the only way in which a matrix can be decomposed, right? You've already, for example, in earlier weeks, you've already seen, for example, LU decomposition, right, or diagonalized decomposition. In each of these cases, there are some conditions. Not every matrix can be written in LU form, right? Not every matrix can be diagonalized. So the fact that any matrix can be written in a slightly simpler form, right, a unitary matrix and an upper triangular matrix, well, that helps, right? That helps us understand the matrix in a slightly easier manner. Okay, so sometimes when solving systems of linear equations, instead of solving the matrix times x equals a vector, we instead take a Schur decomposition of the matrix and then solve it that way. Why? Well, sometimes solving the Schur decomposition system of equations is for some reason a little bit easier than solving the original equation. Okay, so at this point you should just view it as, okay, here's a definition. Okay, if you can write a matrix as U upper triangular, U dagger, then that's called the Schur decomposition, and any matrix can be written in this form, which is a theorem, right? So I would view it as a definition and theorem. Did that help? Yes, yes. So in the video, we showed you, so in the Schur decomposition video, we showed you that any matrix can be written in the form of a unitary, upper triangular, unitary dagger. Yeah. Okay, good. Any other questions? Thank you for being the first, by the way. It's always tricky being the first. Yeah. Okay. I mean, I'm sure there are actually other questions, but that's okay. So we'll be around to help you guys. Okay. So while the TAs are distributing the exercise sheets, let me quickly just walk you through these exercises. And again, all 9 questions, all the first 9 questions you can, in fact, actually all the 11 questions you can and should post on Piazza. The first 5 are a little bit more calculation based. and the next four, the next five, six are more conceptual. So the first one says find four unitary matrices such that U square is equal to the given matrix. Okay, so it's like kind of trying to find the square root of a given matrix, and this will just help you. There's a hint given as well about certain complex numbers. Okay, because you haven't really studied complex numbers, but at least elementary complex numbers we're already making you think about, right? So anyway, this helps you find, this question just helps you think a little bit about unitary matrices. Okay. The second question asks you to find the orthogonal complement of a two-dimensional vector space in a four-dimensional vector space. So really, this is just like solving a system of linear equations and trying to find the null space of a system of linear equations. So it shouldn't be too bad. Here's a hint for question number 3. So question number 3 asks you to find the Schur decomposition for a matrix, and question number 4 asks you to find the Jordan canonical form for that matrix. Actually, both of these can be done in exactly the same way. If you find the Jordan canonical form, that is also a Schur decomposition. Okay, so if you notice that, then that will make it easier. Question number 5. So to compute the singular value decomposition, it should be actually quite straightforward to do it using maxima. Okay, so I mean, it's like in this case, you have to find the eigenvalues. So this is a 4×3 matrix. So once you take the matrix C transpose, you'll get a 4×4 matrix. But with maxima can easily find eigenvalues and eigenvectors even for 4×4 matrices, right? So you really should use that. So for each of these 5 questions, you can and should use maxima if that helps you. Okay. Now question number 6 asks you to prove that if you have distinct eigenvalues, then the corresponding eigenvectors must be linearly independent. Okay. Now notice this is a generalization of one of the questions we asked you in an earlier week, right? I think last week we asked you to show that if you have distinct eigenvalues of a symmetric matrix, then they are linearly independent. Here, we're not saying it's a symmetric matrix. We're saying it's a general matrix. So for a general matrix, prove that if you have distinct eigenvalues, then they must be linearly independent. We're not saying orthogonal, but at least linearly independent. Okay. Yeah, this will take some thought. Now, question number 7 asks you to think about a strange object. So it asks you to think about a matrix exponential. Okay, and this matrix exponential is defined as, so it's just defined formally in the same way as an exponential function would be defined, right? As a Taylor series. So we just take the same formula and now replace x as a variable with x as a matrix. We just pretend that we have powers of that matrix x divided by factorial, the corresponding factorial, summed it up. So infinite summation like this. Okay, and this is going to be our definition of a matrix exponential. Now these matrix exponentials are not just abstract quantities. When people are trying to solve the Schrodinger equation, then actually these matrix exponentials show up all the time. Okay, so that's why understanding matrix exponentials for people who do physics is quite useful. So anyway, in this question, we asked you to prove that if x is Hermitian, then the exponential of x is also Hermitian. And if x is skew Hermitian, then the exponential of x is unitary. Okay, so useful properties about matrix exponentials. And these are related to, for those of you who read about these things, these are related to so-called Lie algebras and so on. But you know, that's advanced topics we won't cover here. Okay, question number 8 is a generalization of the spectral theorems that you guys studied in class. Okay, so sorry, in the videos. So in the videos, we gave you a spectral theorem for symmetric matrices. So symmetric matrices are unitarily diagonalizable. That's what we proved to you in 2 videos, right? But actually, even if they're not symmetric or Hermitian, even if they're so-called normal. So what does normal mean? Normal means A dagger times A dagger A is equal to A dagger. Okay, so the transpose conjugate of a matrix times itself should be equal to the matrix times its transpose conjugate. If so, then it's called normal. So you can check that Hermitian matrices satisfy this, right? But there are other matrices which are not Hermitian, which also satisfy this. And this, it turns out, is a necessary and sufficient condition for a matrix to be unitarily diagonalizable. This is a necessary and sufficient condition for a matrix to be written and in the form U D U dagger. Okay, so for a matrix to be written, for us to be able to write a matrix as a unitary matrix, which is a rotation matrix, right, times a diagonal matrix times the transpose conjugate of that unitary matrix times the inverse of that unitary matrix, it's necessary and sufficient that the matrix A should be normal. And this question asks you to prove that. It gives you a hint as well. So the hint asks you to think about the relationship between T dagger T and T dagger. Okay, so the transpose conjugate of T with itself multiplied in the two different manners. Can you say anything about the relationship between these two? Okay, here's a hint. Well, just try different things. You'll see some relationship between them. Like try a few examples for matrices like this to see what properties these matrices must satisfy for an equality like this. Then I think you'll get some ideas. Okay. Now question number 9 asks you to say something about singular value decompositions. So the singular value decomposition turns out, okay, so it says that, okay, so suppose someone gives us a non-square matrix n by n, okay, and we find so it's a rank R matrix, and we find the first R singular values, the non-zero singular values of that matrix. So these singular values turn out to carry important information about a so-called least square solution. So what is a least square solution? So in general, like your matrix A, it need not be square, right? So you have an m by n matrix. So you may have many solutions. You may have infinitely many solutions. If m is less than n, or in particular, if the rank of the matrix is less than n, then you may have infinitely many solutions to an equation like this, right? So what this question tells you is, suppose you want to find this of the infinitely many solutions, you want to find the solution which has the smallest norm, which has the smallest magnitude, then it's related to the singular value decomposition. Okay, just geometrically, what is this saying? Again, we'll discuss this more when we're actually discussing solutions. But suppose the infinitely many solutions to these equations fall on some hyperplane like this, then trying to find the smallest norm solution, trying to find the solution on this hyperplane. So these are all solutions to that equation, but the one which has the smallest magnitude is the one that we are the most interested in. Okay, why might we be the most interested in this? Well, it's kind of like maybe you've heard of Occam's razor. Who here has heard of Occam's razor? Occam's razor. Has anyone seen this phrase before? Occam's razor? No. So, oh, one person has. Oh, William. So, how would you describe it? Okay, if you don't, so what William just said is, if you don't have the necessity to have a concept, you should kick it out. Let me say it differently. If there are many different possible answers, the simplest answer is often the right one, right? There's no law like this, but we often see that this is the case, right? So in this example, there are infinitely many solutions, and maybe the smallest solution is the likeliest one. Right? So sometimes in engineering problems, this happens to be the case. There are many solutions, but the one with the smallest energy is likeliest to be the answer, or other things like that, right? So could you just repeat in Chinese, if there are many solutions, then the simplest one is often the right one?
就是其实应该不用 repeat， 大家都听得懂嘛。就是有很多 solution 的话，最就是 simplest 的那个就是好的，就是对的，
Okay. You said no need to repeat, but that's okay. Like sometimes my accent is a little bit complicated, and I think there's value in seeing that. So anyway, that's what Occam's razor says. You can look it up. But the reason why this is useful is because sometimes we are interested in the smallest non-solution, the smallest solution. Okay, so that's what question 9 is about. So question 10 is related to that as well, and question 11 is proofs of the Jordan canonical form, but we leave these discussions to the Piazza Forum because there's already enough for you guys to digest, okay? All right, so yeah, we're already at 5 o'clock, it's half an hour into the class, so let's give you guys enough time to try the questions. So the TAs have already distributed the exercise sheets? Yeah, okay, fine. So at this point, the TAs and I will walk around and help you guys with any questions that you may have, okay? There is not actually a separate object. This is artificial object. So what do you know about what do you know about the annual values of commission? And in fact, the student I just said that so given these two facts,
Yeah, but there are cases, for example, if you have more than there are cases where each two of them are linear. Just dependent. You only have two vectors. What if you have
So you mean just not two more than one eigenvectors?
But if you write down the equations just like this, you can prove this. 要找一个后来的话是把它丢掉，然后这样就这样，然后你再找这样，然后这个里面有个地上放，你要找你要去哪里？这个然后这个该导数的，还有一个，对，还有一个。老师让我在里面再加一个3，前面几个月因为所有东西都是他们都出来了，老师让他们现在是老师嘛，就是是歪嘛，这个对，但是因为这个不是。这你这边有想到吗？就比如说你这边选，你这边找到了一个方向，那么剩下这个因为你这个能表示什么？不是你刚才他说的，就是它是有一个应该是这样。这道3。 你现在要找的来我是像这样找一个像跟这两个字这两个位置，这个东西来扫，扫问题。
哇，我都到。
对吧？你看这个 both
So if you already found the first solution, then you can write the same exploit. And now there should be the rank of this, there should be two solutions. But you're now looking for a solution which is a vector which is independent of the solution already. So that's
海贝，不，一个是 B 的，贝
in this example, so what you have to do when you're trying to solve it is to make sure that you check like the y that is checked is the correct one. How do you know? You don't know. So you have to try both.
这里面比别的靠谱的，你这个是在两个是两个色，也是两个人。那你说那个任意的，那个还是不是一个靠谱的？不是系统靠谱的。这个算它问题是
So what are the two items that you want? Both of them, the last one then cannot be What we should be something the matrix is pretty. So now the minus 9 times and then how do you do from here to here? What do you do here? But you never do Russian integration when finding the eigenvectors. The eigenvectors of the matrix may be different from the eigenvectors after you do Russian integration. They may not be the same. So just for this matrix, now you have to check this times x vector could be equal to either the first eigenvector or the second eigenvector. So in this case, then you would have to look at the square times equality should equal 0. And that vector would also be linearly independent from the vector that you that's a very valid point. That looks like it's taken.
要找一个就是从这个方法上我找的两个方法，反正我在一起这个态度方面，这个他没说，就是说他是说我们找到他是 对了，第3题还可以。
我是希望能够证明它是会流线嘛。然后我在他们俩旁边不说那个。相当于我就是拿出他的第 J 页，这个。但是我想证明趋势。相当于我就是看起来很简单，但是往下推就是那你这个的话，唯一是就相当于就是它的话，零出一列乘以这边的一行，同样的零出，一样的是两边各自一定是之前他们俩就可以，因为他们是triangular的话。对，就你就相当于你是一个上三角的所以说你是需要取得一个列表，所以说它就写对上去，然后你是取出一个列，这样子，然后你两个要相乘，这个乘这个的话就相当于一行一行的看，这个乘这个是虚乘，所以说你可以一行一行，每一行都要相乘。那你这一行乘进去的时候，你全部都能看。然后你就是我这个矩阵我可能这个前一个，那就我是想说这个 upper triangle 的矩阵的话，它是一个我没有一行是什么。那样的话，那你不可能这个就是那几行。那你然后一路推到 TJJ， 是一路推下来的话。因为它这里只有到 TJJ 的时候，这边才会有，所以说 TJJ 以前全部是零。然后你沉进去的话，把这个沉进去，就变成这样一个弯的。然后呢，你就会发现前面这都是零。那这里的话，你 TJJ 不可为零啊，你为零的话，你这个矩阵已经是一个零码。那我零，那你只有 T1、T3。然后你就证出来的是 T， 人家是好，写的对吧？不是啊，你有一边不好正，但你放这个正的正，因为你已经把它竖定了，换掉。还是没人写一下。我是你写法，这人说是我应该写的。
但是这个东西不是完全它证明了它在这里碰到了这个，碰到了这个行业，然后它说Decarbonization 它可以对了性，但是这两个东西完全不一样。
第这一行，回馈动作不是这个。需要看这个。
要么这起码一个意思是反正这个东西是在政治的里面的一个推广情况，然后再是这个，那它政治的
Whether it's
I mean, if it's interesting, then basically, so what's posting? What is it?
it should be that
最原始证是
Yeah, difference. Okay, but that's interesting. So using this to improve question analysis.
They ask us to that literally or academics or these matrix or such as number one. Another one is one all this one is but this you have to consider that for another one there's also a lot of
So let's suppose I give you a matrix, let's say 4 by 4 matrix, and it has eigenvalues lambda 1, lambda 1, lambda 2, lambda 3. So notice what I'm asking you to do. So let's say corresponding to the first lambda 1, there are 2 eigenvectors. Let's call them x11, x12. Sorry. As long as you're system maybe
such as there's one or another one maybe this kind of
好像它
Yeah, because of that, and another corresponding different
这样卷。
没有，我在跟上次
他们既然成绩相等以后，单拎上面相当于然后这个是这个样子，然后你从第一行开始，你做这个问题是完全的，但是作为一个传统的学员，没有拿然后。那你对这里 DEJ 一直到 TJ 减，你这个有点用了，因为你这里只有在你这里的话用这个19这也是类似，你是从这里 TJJ 开始，你这里才会所以说只有 TJJ 的时候开始，这里才你这里走过去，这里才能过去，所以说可能这一减1之前。然后就是，那你看这个喽，你本来就是这减1出来都是没有，那就是有没有去打竖看的话，在这里上面说没有，然后你也还可以打看，能看的话就看后面，能看的话我从 J 把 J 提进去，因为后面都是一图嘛，我把 J 提进去之后呢，J 行的时候会变成这样子，而且这样子的话。其实前面能够证出来就是 DEI 是等于，但是这个的话跟你证数的是一样的。看后面，看后面的时候就是，你这边就在这个等于什么呢？相当于你相当于这一些存在，然后就相当于你的证，这个的话是 T 的嘛，它的，
就是这个东西是
相当于打红证它后面，然后就。对，打数都特别像，只有这个。但是这样写还是有误会的。我就这样子。我建议是讲是拿 I 跟 I 对，你逃不过的 I 跟 I 跟 I 跟 I 这两个找到另外好像是这样子，他每次同一个矩阵。把它那个把它留一个值，把下面的值直接换成就一个一个，它是一个完整的矩阵，它是先指一个矩阵进去，把这个矩阵变成一个矩阵，把这个再成一个矩阵，把这个矩阵变成一个矩阵。然后，但它有个问题就是，我用 base 然后导致就是反正有问题。没有，然后 那还需要调整的是哦，actually，我知道了，其实我们做的是多种。QR 它主要是这个主要是 distribute。But actually we can do it. 找到一个要找一个中间。